We feed language models more data, scale their compute, and apply rigorous reinforcement learning, yet they continue to generate authoritative text that is entirely false. Even in the simplest settings, answering fact-based questions with clear ground truth, frontier models fail with complete confidence. The prevailing assumption across the industry is that scaling will eventually solve this. The logic suggests that by ingesting more training data and extracting better probability scores, models will naturally stop hallucinating. Scaling alone cannot overcome a fundamental bottleneck: the mapping of finite model weights to an infinite variety of real-world facts. Mathematical diagonalization arguments prove that no computable model can universally verify the truth value of everything it generates. This is a structural ceiling. This scatterplot maps the industry, pitting a model's usefulness, how often it attempts an answer, against its factual reliability. Most frontier models are heavily optimized for maximum output. They attempt to answer almost everything, yielding high utility, but carrying unacceptably high error rates. When engineers adjust the guardrails to force strict factuality, the behavior shifts. To avoid errors, the model aggressively refuses to answer, severely crippling its practical usefulness. Notice the top right corner. High utility combined with near-perfect factuality remains completely unpopulated by any current architecture. This empty space represents the discrimination gap. It is the model's inability to cleanly separate the knowledge it actually possesses from its own confabulations. Reaching that top right quadrant requires abandoning the pursuit of zero overall errors. The engineering target must shift from eliminating hallucinations entirely to eliminating confident errors through metacognition. To understand why confident errors persist, we have to look past the generated text and examine the statistical confidence scores operating under the hood. During generation, a model assigns a probability to its outputs. If a model has perfect statistical calibration, an aggregate confidence score of 60% means it is correct exactly 60% of the time across a massive set of queries. A common engineering assumption treats perfect aggregate calibration as the ultimate fix for hallucinations. Calibration only measures the average. It ignores discrimination, the model's actual ability to isolate a correct output from an incorrect one on a specific case-by-case basis. This diagram illustrates the internal confidence distribution of a perfectly calibrated model, plotting correct answers in green against incorrect ones in red. While the averages hold up mathematically, the distributions overlap severely, particularly in the middle confidence ranges. Because of this heavy overlap, the model's internal statistical state cannot differentiate between a correct answer with a 0.6 probability and an incorrect answer with a 0.6 probability. Without high discriminative power, perfect calibration is useless for reliability. The system knows its overall error rate, but remains entirely blind to which specific outputs are the errors. This statistical blindness creates a severe penalty when engineers try to enforce a strict low error rate, like a 5% threshold, on a model with poor discrimination. This line graph calculates the exact operational cost of eliminating those hallucinations through forced abstention. To guarantee a 5% error ceiling, the system has to discard huge clusters of data where correct and incorrect answers overlap. Getting the errors down to 5% requires dropping over half of the valid correct outputs. That 50% loss of correct information is the utility tax. Commercial AI providers optimize for engagement and coverage, so they routinely refuse to pay it. Avoiding the utility tax requires a different engineering objective: faithful uncertainty. Consider a standard factoid query, such as identifying the birthplace of Barack Obama. The first metric is intrinsic uncertainty. This evaluates the raw statistical variance of the weights. It measures the mathematical probability that the model will generate conflicting answers across repeated samplings of the same query. The second metric is linguistic uncertainty. This tracks the actual text the model returns to the user, the explicit verbalized hedging and qualifiers present in the final output. Faithful uncertainty demands absolute alignment between these two metrics. If the intrinsic statistics show high variance, the output text must reflect that exact variance through explicit linguistic doubt. When verbal output accurately reflects internal statistics, an error stops being a hallucination. It becomes a clearly marked hypothesis. This preserves the volume of information the system provides without betraying the user's trust. The industry is currently shifting toward agentic AI, connecting models to external tools like live web search and document retrieval systems. A common engineering objection suggests that if a model can simply search the internet for a missing fact, mapping its internal uncertainty is a waste of compute. External tools do not resolve the discrimination gap. They merely hide it behind high scores on retrieval benchmarks. Access to tools solves the problem of data storage, but it introduces a far more complex problem of data control. This schematic illustrates the standard architecture of modern AI agents, connecting the base language model directly to the external tool harness. Operating without internal metacognition, the harness flies blind. It triggers constant, inefficient searches, even when the model already has the correct answer. Worse, it creates sycophancy. An unaware model will blindly accept retrieved context from the web, even if that incoming data is deeply flawed and contradicts the model's own highly accurate internal priors. Without a mathematically grounded sense of self-doubt to weigh incoming information, an autonomous agent is incapable of safely managing external data. Solving the agentic control problem, we insert a metacognitive control layer between the model and external tools. It serves two functions. Introspection acts as a gatekeeper, invoking searches only when intrinsic confidence drops below a threshold. Regulation actively weighs returned data, rejecting external input mathematically weaker than internal priors. The immediate challenge in building this layer lies in the alignment process itself. Standard post-training techniques push models to adopt a decisive, helpful tone, effectively erasing the subtle uncertainty distributions required to make the math work. Engineering metacognition requires developing post-training algorithms that maintain behavioral guardrails while strictly preserving the raw statistical honesty of the base model. The system must learn to follow instructions and interact naturally, all without overriding its own internal sense of doubt. Expanding an infinite database of facts is no longer the sole objective. The future of autonomous AI depends on architecting self-aware systems that can faithfully communicate the exact boundaries of what they know.